Okay, so continuing on with our lecture for Unit 1 or Chapter 1, we're now going to talk about methods and devices to measure volume. And we're going to talk about some of the common pieces of volumetric glassware. So volume, just as a refresher, is the space occupied by matter. Okay, so here we have a nice picture of all of the different pieces of volumetric glassware. So they're labeled A through F. So let's talk about each of these pieces of volumetric glassware and their purpose. So a beaker, which is shown with the letter A, is used for imprecise volume measurements. The graduated marks represent relatively large volumes. Option B is a barrette, shown here with the letter B. A barrette is used and has a very specific purpose. It's used for precisely dispensing a variable amount. Option C in yellow is known as a volumetric flask. It has one graduated mark, and this graduated mark represents a precise volume. So although you can't fill a volumetric flask halfway and take a precise measurement, volumetric flasks are wonderful for preparing solutions and performing dilutions because you can generate and you can measure an exact volume to a high level of precision. So a volumetric flask precisely measures a fixed volume. For example, 100.00 milliliters. A graduated cylinder, shown with the letter D, graduated because it has these graduated marks. Now, students love to say the graduated cylinder is a precision piece of glassware, and in reality, a graduated cylinder is useful for dispensing a variable volume with a medium level of precision. It is not as precise as a barrette or a volumetric flask, but it is commonly used if you just need to dispense a rough volume of liquid. Option E is known as a volumetric pipette. It's used to precisely dispense a fixed volume. So again, just like a volumetric flask, it can be filled and it can dispense a precise volume. For example, 10.00 mils, for example. The last and the least, in my opinion, is the Erlenmeyer flask. It's used for imprecise volume measurements. An Erlenmeyer flask is often chosen over a beaker in cases where you need to mix liquids. Beakers are primarily used for pouring. So these are the different pieces of volumetric glassware, and we're going to talk about how to read volumes using volumetric glassware now. Any questions so far? So this is just an overview, and this will be really useful in the laboratory because if you can identify the piece of glassware that you're using, you can very quickly take measurements using that piece of glassware. Any questions I can address? Okay, let's continue on now. So let's talk a little bit about measuring volumes. So you measure the liquid volume from the bottom of the meniscus at eye level. Now, what is the meniscus? A meniscus is a curve formed as the result of a liquid interacting with the container. Now, in this class, your meniscus will always be concave. If you see a convex meniscus, you're either dealing with an organic compound or you're dealing with mercury, neither of which are particularly fun to handle. Now, Here's an example of a graduated cylinder. If we zoom into the meniscus, we can see the liquid meniscus layer. And at eye level, we're always going to measure our volume from the bottom of the meniscus. So we're going to very clearly mark, let me use a very bright pen for that. We're going to very clearly mark the bottom of the meniscus. That's the bottom of our liquid curve. And now we're going to take our volume reading from the bottom of the meniscus. Now, just like before, this is a graduated device. So we have to follow our standardized procedure. First, we figure out the value of a graduated tick. We identify the allowed precision, 1/10 of a tick, and we report all of our certain and estimated digits. So to go from 8 to 9 milliliters, it takes us 10 ticks. So as a result, we know 1 milliliter is equal to 10 ticks. So in other words, 1 tick is equal to 1/10 of a mil, in other words, 0.1 mil. For 1/10 of a tick, we in turn get 0.1 over 10 mils, which gives us 0.01 milliliters. So we can estimate up to 1/10 of a tick, and we measure our volume from the bottom of the meniscus. Would someone like to tell me? Would someone like to take a guess for the volume measurement inside this graduated cylinder? 8.31, that's a good guess. That's wonderful. That's a great measurement. So one thing I'd like to highlight, 8.3, these are our certain digits. We know that our meniscus is slightly above the definite graduated mark, indicating 8.3 milliliters. Note, there's going to be some variation in your last digit. So you can report 8.33 milliliters, and that would be a perfectly fine measurement. Because remember, the last digit is estimated. Does that make sense to everyone? So volumetric glassware is almost identical to other graduated devices. The only thing that's new is that you have to measure the volume from the bottom of the meniscus at eye level. Any questions on this example? Any questions on this example? Wonderful. We're now going to look at a piece of glassware that often gives students a lot of difficulty. And these are called barrettes. Now, just looking at a barrette, does someone notice something odd about the graduated marks in a barrette? Does anyone notice anything odd? So if we look at our graduated cylinder, it counts from 0 to 10 going up.
The number 0 start from the top instead of starting at the bottom.
Exactly. I like to think of a barrette as a graduated cylinder flipped upside down. So 0 is on top and typically 50 is on the bottom. So a barrette is measured from top to bottom because a barrette tells you the volume dispensed. So as always, you read the bottom of the meniscus at eye level. So we've noted the bottom of the meniscus. And let's fill in our tick mark. So here's 30. This next tick would be 30.1, 30.2. And then to unpack this further, let's look at the value of a tick mark. So to go from 30 to 31, so in 1 milliliter, it takes us a total of 10 ticks. In other words, 1 tick is equal to 0.1 milliliters. Okay, so counting, we see that the bottom of our meniscus is between 30.2 and 30.3. So we'd write our certain digit as 30.2. And are we done here? Are we done here? Is 30.2 milliliters an acceptable measurement? So I see in the chat that some students are reporting an additional digit. Remember, we can report all of our certain digits. So these are our certain digits. And then we can estimate up to 1/10 of a tick. And in this case, 1/10 of a tick is equal to 0.1 milliliter over 10, which in turn gives us 0.01 milliliters. So we report our certain digit and then we estimate one additional digit. So 30.25 would be our full measurement for the volume inside this burette. Does that make sense to everyone? Any questions on this example?
I have a question about, so when we read from bread, we read how much is dispensed, not how much is already in there left, right?
Yeah. So this 30.25 is telling us that 30.25 milliliters of liquid has been dispensed from the burette.
Okay.
And that's why we see this blank space before 30.25. This is just air that is taking the place of the liquid that we've allowed to escape the burette.
Okay, thank you.
Perfect, perfect. Any other questions I can address? So let's keep going now and let's do an example. Let's do an example. So I'd like us to take a moment and given the following picture of a burette, I'd like you to tell me which of the following burette measurements are correct. So this is found on page 40 of the Unit 1 notes. Let's take about 2 to 3 minutes and let's try to get some responses in the chat. Remember, burettes are measured from top to bottom. The top is 0, the bottom is 50. And we already start to see some responses in the chat. Just make sure, let's try to get a few more responses before we discuss, and just make sure you're checking the amount of sig figs that you can report. And remember, you can report up to 1/10 of a tick. The responses I'm seeing in the chat look great so far. Everyone seems quite comfortable with this idea. This is very good, since that means for the measurements lab, everyone's going to have quite an easy time taking their measurements. Let's give everyone about another minute, and don't be shy to share your proposed response. Even if there's a disagreement between you and your classmates, that doesn't necessarily mean that your responses are incorrect. So let's discuss this example. So our 24 mark is right here. The bottom of our meniscus, I'm going to mark in light blue. We always measure our volumes from the bottom of the meniscus. And looking at our tick marks, we're past the first and we're almost right on the second tick mark, okay? We know that going from 24 to 25, so 1 milliliter is equal to 10 ticks. So then 1 tick is equal to 1/10 of a mil, which is 0.1 milliliters. We're at the second tick, so this corresponds to 24.2. However, we can estimate up to 1/10 of a tick, and we know 1/10 of a tick is equal to 0.1 over 10 mils, which gives us 0.01 milliliters. So then we'd report our final measurement as 24.20 milliliters. And the responses I saw in the chat are great so far. Any questions on this example? Any questions on this example? Okay, let's do another one. Let's do another one. This time we don't necessarily have a burette, but we do have a graduated cylinder at play. So let's take a moment and let's try to record the following volume measurement for the following graduated cylinder. So let's take about 2 to 3 minutes on this example. And then we'll discuss. And we already see some responses in the chat. Let's try to get a few more responses in the chat before we discuss. And again, don't be shy sharing your response, as it helps me understand where the class is at in this problem-solving process, and it helps me provide more focused and structured feedback. You see an array of responses so far. Let's give this about another 1 to 2 minutes. And then we'll discuss. And just remember, try to identify whether you're dealing with a graduated cylinder or a burette, as some of the responses I see would be correct if this were a burette, but I would just check how the tick marks are arranged. And we'll discuss in about another minute. Okay, so first and foremost, if you're ever dealing with an unfamiliar piece of glassware, you try to see whether your graduate marks are counting up in increasing order or down in increasing order. If it's counting up in increasing order, this is known as a graduated cylinder. If it's counting down, you're looking at a burette. So as we can see, we very clearly have a graduated cylinder. 0 is at the bottom, 11 is at the top. So then, let's now figure out the value of a tick. So to go from 10 to 11, which is 1 milliliter, it takes us 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1 milliliter takes us 10 ticks. So then 1 tick is equal to 1/10 of a mil, which is 0.1 milliliters. While we're here, let's figure out the value of 1/10 of a tick, which is 0.1 over 10, which gives us 0.01 milliliters. Okay, from the bottom of the meniscus, oops, one moment. From the bottom of the meniscus, let's quickly mark that in light blue. Okay, so the bottom of the meniscus is slightly above the 1, 2, 3, 4, 5, 6 mark. So for our certain digits, we'll report 10.6, and then we can estimate an additional digit. So we can say 10.67, for example, milliliters. So this would be our complete measurement for the volume of liquid in this graduated cylinder. Does that make sense to everyone? Does everyone see how this is a graduated cylinder and not a burette? Perfect. Any questions I can address on this example? Yes, essentially any variation in the last digit would be accepted. You'd get full credit as long as there are certain digits are correct and you're within the natural variation of your measurement, which is based on your estimated digit. Okay, so let's keep going now, and let's talk about significant figures in the context of calculations. So this informs how to write answers properly in Canvas. So a digit is significant. A digit is significant if, now there are two different conditions. First, non-zero digits are always significant. They're always considered significant digits. A zero is significant if, one, it's between non-zero digits. I like to call these sandwich zeros because they're sandwiched between two numbers. So for example, 107, we'd have a total of 3 significant digits because 1 and 7 are significant, and this 0 is between non-zero digits, so it's also significant. So this number would have 3 significant figures. The second case where a 0 is significant is if that 0 is at the end of a number and after a decimal point. So it has to meet both of these conditions. So for example, this 0 that is after a number and after a decimal point is significant. Another example of this would be 5.0. As we can see, if we look at the 0 at the end of 5.0, it is clearly after a number and it's after a decimal point. So this number would have 2 significant figures, 5 and 0. A 0 is not significant if it is before the first non-zero digit. I like to call these leading zeros. So for example, if we have 0.005, these 3 zeros that are before our first non-zero digit are not significant. The only significant digit would be our 5. So this number would have 1 significant digit or 1 significant figure. The last case where a 0 is not significant is if it's at the end of a number but not after a decimal point. I like to call these zeros trailing zeros. So for example, at the end of 170, it is at the end of a number, but it's not before or after a decimal point. Let's add, so it's not before or after. So for example, 5,000, these trailing zeros are not significant. And as a result, this number would have 1 significant figure. So there's a special type of number that we need to talk about next, and these are known as exact numbers. Exact numbers are conversion factors or numbers obtained from counting. And exact numbers have unlimited significant figures. So for example, 2.54 centimeters per inch, this is a conversion factor, and this is an exact number. So for the purposes of counting sig figs, we think that this number has unlimited significant figures. Another example that comes up very commonly in chemistry is if you're looking at a molecular formula and you count, for example, 2 hydrogen atoms. Since this 2 is obtained from counting the number of hydrogen atoms, this number obtained from counting is an exact number. The idea of when you're counting objects, the idea of there being half of an object or any uncertainty in the number of objects counted does not make physical sense. Another example is if I count the number of people currently in our call, we see that there are 23 people in our call, right? Now, there's no uncertainty in that number because it's a number obtained by counting. It's not 23 people plus or minus one student or anything like that. So exact numbers are numbers obtained from counting or conversion factors. And exact numbers have unlimited significant figures. Does this make sense to everyone so far? Is everyone comfortable with these rules so far?
What do you mean by unlimited significant figures?
So essentially, as we'll talk about when we start performing calculations following significant figure rules, exact numbers will never affect, will never reduce the amount of significant figures you can report in your final answer from calculations. So exact numbers do not affect the precision of your final answer. And the really useful thing about exact numbers, especially in the case of conversion factors, is that the significant figures of your input will not change significantly during calculations involving exact numbers. So the simplest way I can put it is that unlimited significant figures means that when you perform a calculation involving an exact number, you will not dramatically affect or change the significant figures in your final answer. Does that make sense? And we'll see how this works in practice in a moment, actually. Are there any other questions that I can address? So first, let's start to apply these rules, and let's look at the following set of numbers. Let's indicate how many significant figures do each of these numbers have. And as a bonus, let's write each number in scientific notation. So I'll do these first three examples and you'll do the second set of three. So looking at 5.07, so 5 and 7 are automatically significant figures, and this 0 is after a non-zero number and after a decimal point, and it's between non-zero digits, so this 0 is significant. So this number has 3 significant figures, and in scientific notation, we just write this number as 5.07. There's no need for any modification. So let's look at this next number, 0.0876. So looking at this number, we have some leading zeros. So zeros before the first non-zero number. Leading zeros are not significant, and all of our non-zero digits are significant. So this number would have 3 significant figures. And if we wanted to write this number in scientific notation, we'd have to move our decimal point a total of 2 spaces to the right, and that would give us 8.76 times 10 to the negative second. Now, as we notice, and this is why I like scientific notation, when you write out numbers in scientific notation, it gives you a lot of insight into the number of significant figures. And numbers in scientific notation are much easier to read and figure out the number of significant figures in that measurement. As we can see, we have 1, 2, 3 digits. So this 8.76 times 10 to the negative second has 3 significant figures. Let's do one more example. So 1,560. Okay. As we can see, we have a 0 that is after a non-zero digit, but neither before nor after a decimal point. So this 0 is not significant. Our first 3 digits are. So this number has 3 significant figures. And if we're writing it in scientific notation, 1,560, we'd have to move our theoretical decimal point 1, 2, 3 spaces to the left, and that gives us 1.56 times 10 to the third. And as we can very clearly see, this 1.56, now that we've gotten rid of this trailing zero, 1.56 has 3 sig figs. Now, it's really important that you pay attention to the decimal point. So if we're looking at 1,560 with a dot at the end, this dot should not be overlooked because placing a decimal point changes whether a zero is significant. Now, looking at this new number, if we place our decimal point at the end, this zero is after a non-zero digit and it's before a decimal point. So it's treated like a sandwich zero. So this zero is significant. So in this case, simply placing a decimal point at the end of our number gives us a number with 4 significant figures. So it's really important that you pay attention because 1,560 is very different than 1,560 with a decimal point at the end. The decimal point determines and can affect whether or not a zero is significant. Do these examples make sense to everyone? Sure, we can do that. So a student in the chat was asking, how do we write 0.8760 in scientific notation? Well, these 4 digits are significant because this 0 is after a non-zero number and after a decimal point. So we would write this after moving our decimal point 1 space to the right, we get 8.760 times 10 to the negative first, retaining the fact that we have 4 sig figs. This was just a question that a student asked in the chat. Any other questions that I can address? If not, let's continue on and let's now have the class work on the following 3 examples. And I'd like you to tell me how many significant figures each of the following numbers have and to write each of these numbers in scientific notation. So I'll label these 3 examples A, B, and C, and I'll give everyone about 4 to 5 minutes. Let's go with 5 minutes to give everyone enough time to work through these examples, and don't be shy to submit your responses in the chat. So looking at the chat, we see a range of reasonable answers. Let's try to get a few more responses in the chat. One thing to be really careful about is that when you're converting your number to scientific notation, make sure you're moving your decimal point so you end up with a number that is greater than or equal to 1 and less than 10. And the responses I see in the chat are looking great so far. Let's try to get a few more responses and then we'll discuss as soon as we can. And the responses I'm seeing in the chat look great. Let's give everyone about another 2 to 3 minutes, and then we'll discuss. Just so that way students can work through the problems, draw their own conclusions, and share their responses. We'll give everyone about another 1 to 2 minutes to compile their responses. The responses I'm seeing in the chat look great so far. Just make sure your exponent is correctly noted. And I noticed that some students have already corrected their exponent based on that feedback. Wonderful, wonderful. Let's try to get a few more responses and then we'll discuss in about another minute. And I'm really pleased to see that everyone's following along with this content. So let's now get started with the first example. So 90.980, so we have a sandwich zero that's between non-zero digits, so that's significant. All of our non-zero digits are significant. And this last zero is after a non-zero digit and it's after a decimal point. So 90.980 has a total of 5 significant figures. So if we move our decimal point 1 space to the right, we get 9.0980 times 10 to the first. Now it's really important that your number in scientific notation have the same number of significant figures as your longhand or long form number. And as we can clearly see, in scientific notation, we can clearly see we have 5 significant figures. Let's look at this next example, 0.009830. So let's write that out. So first and foremost, we have some leading zeros. And as literally everyone who submitted a response in the chat has noted, these leading zeros are not significant. However, we have a zero that's after a non-zero digit and it's after a decimal point. So this last zero is significant. So we have 4 significant digits. And to make this really easy to see, let's write this number in scientific notation. So we move our decimal point 1, 2, 3 spaces to the right. Sorry, for the first number, it's 1 to the left. Sorry about that. So for this number, we're moving our decimal point 3 spaces to the right. That gives us 9.830 times 10 to the negative third. And as we can clearly see in this case, we have 4 significant figures. Finally, for 10,200, we have a sandwich zero. That sandwiched zero between non-zero digits is significant. These trailing zeros, however, as there's no decimal point at the end of our number, these trailing zeros are not significant. So this number only has 3 significant figures. So to write this number in scientific notation, we're going to place a theoretical decimal point at the end, and we're going to move our decimal point 4 spaces to the left so that we have a number that's between 1 and 10. That gives us 1.02 times 10 to the 4th. And as we can clearly see in scientific notation, our number has 3 significant figures. Does this make sense to everyone so far? So to address a side question, one student was asking 40.0, how many significant figures does it have? Well, this 0 is between a non-zero digit and a decimal point, so it is significant. This last 0 is after a non-zero digit and after a decimal point, so 40.0 has a total of 3 significant figures. And we can write 40.0 as 4.00 times 10 to the first. Did that address the question in the chat? Perfect. Are there any other questions that I can address? If not, let's continue on and let's talk about rounding. So significant figures and calculations, rounding. So in general, this is a general rule. The calculated value cannot have more significant figures than the measured values used in your calculations. Now, when you perform a calculation, inherently, you may end up with a number with more significant figures than you can report in your final answer. Thus, you're going to have to round your answer to the correct number of significant figures. So for rounding, your first goal is to indicate the last significant digit. Then you're going to examine the digit after the last significant digit, and you round down if the digit is 4 or less, and you round up if the digit is 5 or greater. So for example, if we're rounding 13.5232 and we're rounding it to 4 significant figures, we're going to highlight our 4th significant digit, and then we're going to look one space to the right. Now looking at this number, we see that 3 is less than 5, so as a result, we round down. So that in turn would give us 13.52. As another example, if we round 0.01506 to 3 significant figures, remember, these zeros aren't significant, so we don't have to count them. So our 1 is significant, 5 is significant, and this sandwiched 0 is significant. So we are going to highlight this 0, and then we're going to look one space to the right. We're then going to circle this digit, and as we can see, 6 is greater than 5, so then we round up. So as a result, this would give us 0.0151, which it's a little hard to notice at first. So I always like to write numbers in scientific notation, and this would give us 1.51 times 10 to the negative second. And we can very clearly see that these numbers have 3 sig figs. Do these examples make sense to everyone? So make sure you're counting your sig figs carefully. So if we don't have any other questions, let's now take a moment and let's try to round the following 2 numbers to the correct number of significant figures. And we'll discuss this example in about 3 minutes. And I'm already starting to see some reasonable responses in the chat. And let's try to get a few more responses in the chat, but overall, the responses I'm seeing look great so far. You round up if the digit is 5 or greater. The rounding up on 4, I've never seen that convention before. So I'd follow the convention in the notes, as it's far more common in the chemistry series to round up if your last digit is 5 or greater. And the responses I'm seeing in the chat look great. Let's try to get a few more responses and we'll discuss in another minute. And one thing to note when you're rounding, remember that you still need some zeros as placeholders to indicate if your number is very large or very small. Exactly right. Wonderful. So let's try to get a few more responses and then we'll discuss momentarily. Okay. You don't put a 0 placeholder after a decimal. You can, yes. You use the placeholder 0 to indicate a small number if it's a leading 0. And we'll show an example of that actually right now. So 1,350, if we're rounding it to 2 significant figures, 3 is our second significant digit. We're going to look one space to the right. That in turn allows us to look at 5. So 5, we round up. So that in turn gives us 1,400. Note, this number has 2 significant digits with these trailing zeros being used as placeholders. If you want, you can write this number in scientific notation. And that in turn gives us one moment, sorry about that. That gives us 1.4 times 10 to the third. And here, this is why I like scientific notation, because it's very explicit about the number of digits that we can report. Does this make sense to everyone? So you still need your placeholder digits to note that 1,400 is a large number. Just like you need placeholder digits to note small numbers. So if we have 0.005804, if we're rounding to 3 sig figs, these leading zeros are not significant, so we don't have to count them. 5, 8, and this sandwiched 0 between 2 non-zero digits are significant. So I'm going to underline my 0, and then I'm going to look one space to the right. Now, 4 is clearly less than 5. So 4, whoops, sorry about that. 4 is clearly less than 5. So then we round down. And that in turn would give us 0.00580. As we see, this number has 3 significant figures. And we need these leading placeholder zeros to note that we have a small number. We can also rewrite this number in scientific notation, 1, 2, 3, and that gives us 5.80 times 10 to the negative third. And we can very clearly see here, this number has 3 significant figures. Does this make sense to everyone so far? Any questions on these examples?
Professor, I have a question about not the leading zeros in the small numbers. My question was about the trailing zero. Like when we drop that 4, do we need to put a 0 instead to put the place to hold, hold the place for it, or no?
So if you're writing your number long form, so 1,400, for example, you do need these placeholder zeros. In scientific notation, you do not need your placeholder zeros because you're already noting using your power of 10 that you have a large number. It's very key to note that 1.4 has 2 sig figs, and if we add zeros at the end, we would be reporting more significant figures than requested in the problem. Does that make sense?
My question was about the second example, that 4. I'm talking about that last 4 that we dropped. Did we put a 0 instead there? Like we put like 0, 0, 5, 8, 0, 0. The last 0 is my question.
You do not need to put another placeholder 0 because a placeholder 0 is only used to denote whether your number is large or small. And a 0 at the end of a number after a decimal point is not necessary. And further, because we're asked to round to 3 sig figs, if we added a trailing 0, we would have one more significant figure than required.
Okay, got it. Thank you.
Perfect.
Professor, I have a question on the answer you were going over, the 1,400. Yes. Which would be, if we were just to write the 1,400, would that be a sufficient answer, or would we need?
As long as you make sure you do not put a decimal point at the end.
Okay. And only if you ask how we would write it in, what is that word called? Significant.
Long form or as a decimal, both are common ways of writing a number without scientific notation.
Okay, got it. Thank you.
Perfect. So we've talked about significant figures. We've talked about rounding. Let's now start to see how significant figures are handled when you multiply and divide numbers. So when multiplying or dividing numbers, the rule is pretty straightforward. The product, your final answer, has significant figures equal to the number with the least number of significant figures. So for example, 2.0 has 2 sig figs. We multiply it by 3.0, which has 3 sig figs. 2 is the smallest number of significant figures, so our answer has 2 significant figures. Likewise, 600, despite being a large number, only has 1 significant figure. So if we multiply it by 5, we end up with 3,000 with just 1 significant figure. As a shortcut, you retain the least number of significant figures in your 2 input measured values. So let's do an example, and I'll showcase to you how we can combine these significant figure rules for multiplication with our rounding rules that we discussed previously. So in the first case, we have 25 times 4. 25 has 2 sig figs. 4 has 1 sig fig. We punch this in our calculator, we get 100, which has 1 sig fig, so we're good to go. Let's look at 2.59 times 2.0. So 2.59 has 3 sig figs. We multiply it by 2.0, which has 2 sig figs, And that in turn gives us 5.18. Now, would someone like to tell me how many sig figs should I report in my final answer? How many significant figures? The least number of significant figures is 2. So we need to take this number and we need to round it to 2 sig figs. So then I highlight my second significant digit and then I look one space to the right. As I can clearly see, 8 is greater than 5, so I round up and I get 5.2 as my final answer. Let's look at one more example. So we have 2.000 over 3.0. So we have a number with 4 sig figs divided by an answer with 2 sig figs. If we punch this into our calculator, we get 0.6667. And again, we round to the least number of significant figures. So we need to round this number to 2 sig figs. So counting, we don't count our leading 0. We count to our second significant digit and we look one space to the right. Now we can clearly see 6 is greater than 5, so we round up to 0.67. This number has 2 sig figs, and we can also rewrite this in scientific notation for clarity as 6.7 times 10 to the negative first. And we can clearly see that this number has 2 significant figures as required from our multiplication rules. Does this make sense to everyone so far? Any questions so far? Don't be shy to unmute and ask any questions that you have. So just as a recap. So first and foremost, when you multiply numbers, you retain the least number of significant figures from the 2 values that you multiply or divide. In the first example, we didn't have to do any rounding because 25 times 4 gave us 100, which has 1 sig fig. For the second example, 2.59 times 2.0, we see that we have a number with 3 sig figs times a number with 2 sig figs. We get out 5.8. However, we're not done here. We need to round 5.18 to 2 significant figures. We look for our second digit and we look one space to the right. We see 8 is greater than 5, so we round up to 5.2. Does that part make sense? Did that clarify? And let's repeat the explanation for example 3. We have 2.000 over 3.0. We have a number with 4 sig figs divided by a number with 2 sig figs. Our answer, as a result, must have 2 significant figures. So then, we look for our second significant digit, not counting this leading 0, of course, and we look one space to the right. 6 is greater than 5, so we round up. So now that we've seen some representative examples, I'd like you now to take a moment and work on the following 2 examples. I'd like you to complete the following calculations and report your final answer to the correct number of significant figures. And the responses I see in the chat look reasonable. Let's spend another 3 to 4 minutes working through this example. Let's try to get a few more responses in the chat. Don't be shy to share your responses in the chat, and we'll discuss in about another 2 to 3 minutes. And the responses I'm seeing in the chat look reasonable so far. Let's keep working on this example for about another 1 to 2 minutes, and we'll discuss momentarily. Okay, so let's discuss this example. So we have 0.505, sorry, 0.0505. This number has 3 significant figures. These trailing zeros are not significant. We then divide by 5.000, and this bottom number has 4 significant figures. So, as we can see, our final answer then must have 3 significant figures, the least number of significant digits among both of our measurements. So punching this into our calculator, we in turn get 0.0101. And as we can clearly see, this output number has 3 significant figures as required. Let's look at this next example where we have 650 over 1.00. 650 has 2 significant figures. 1.00 has 3 significant figures. So then, our final answer must have 2 significant figures. We punch this in our calculator. We get 650, which matches our 2 significant figure requirement. Any questions on these examples? Any questions on these examples? Don't be shy to unmute and ask your questions verbally as well. Or you can ask your questions in the chat.
Can
Yes.
you go over the 0.0505
Yes.
again?
Mm-hmm. So looking at 0.0505, the leading zeros are not significant. So this top number has 3 significant figures. 5.000, these trailing zeros are after a decimal point and after a non-zero number, so they're significant. So then we have a number with 3 significant figures divided by a number with 4 significant figures. In turn, our answer must have 3 significant figures. So when we punch this into our calculator, we get 0.0101, which in turn, this number exactly matches our requirement as it has 3 significant figures. We can also rewrite this number as 1.01 times 10 to the negative second, and we can clearly see now that this number has 3 significant figures.
Professor, when you got the 0.0101, did
Yes.
we multiply or divide on that?
We divided because the
okay,
we were
that's
asked
what
to perform was division.
okay.
Does that
All
make
right.
sense?
Yes, thank you.
Any other questions I can address? If not, let's continue on and let's talk about addition and subtraction. And addition and subtraction follows an entirely different set of rules. When adding or subtracting, you retain the least number of decimal places. So here's the procedure that I've developed. So you write each number that you are adding and subtracting, lining up the decimal point. If there is no decimal point, you place the decimal point at the end of the number. If both numbers do not have a decimal point, you align the last reported significant digit. You then indicate the number with the least number of decimal places, and you round your final answer to the lowest number of decimal places. So let's look at some worked examples. So in this case, we have our top number with 4 decimal places, our bottom number with 1 decimal place. We do not care about sig figs when adding. We care only about decimal places. And as we can clearly see, the least number of decimal places, comparing 1 and 4, would be 1 decimal place. So we're going to round this number to 1 decimal place. And so since the digit after 7 is 1, it's less than 5, we in turn round down to report our final answer with 1 decimal place. Does this make sense to everyone so far? Now, to really drive home the point that when adding and subtracting, we do not care about significant figures. We care about decimal places. Looking at this next example, 3.000 has 3 decimal places. 175.2 has 1 decimal place. So then we'd round our final answer to 1 decimal place, and we end up with a number with 1 decimal place and 4 significant figures. In addition and subtraction, you can quote unquote gain or lose significant digits in your final answer, because addition and subtraction only cares about decimal places. So let's do some examples. Let's do some representative examples. So for example, we have 5.56 minus 0.5. Okay, I line up my decimal point and then I count decimal places. So I see 2 decimal places in 5.56, 1 decimal place in 0.5. So then my final answer should have 1 decimal place. I end up with 5.06, and now I have to round to 1 decimal place. I highlight my 0, I look 1 space to the right, and I see 6 is greater than 5, so I round up. That in turn gives me 5.1. Let's do another example. If we have 605 minus 105, I put so both of these numbers do not have a decimal point. So in turn, I'm going to circle my last significant digit. So we're going to round our final answer to the same place as our last significant digit. So We subtract 605 minus 105, and that in turn gives us 500. We can report up to the ones place. So in turn, we write our final answer as 500 dot, making very clear that this ones place is our last reported significant place. Let's look at another example. We have 1.07 minus 0.55. Both of these numbers have 2 decimal places. When we complete our subtraction, we in turn end up with 0.52. This number has 2 decimal places, so it follows our addition and subtraction rules. But as we've noticed, we've lost a significant figure. This is normal. Do not worry about it. Now for the last example, we have 1,587 minus 120. Let's make sure that we line up our numbers, and then we indicate the last reported significant digit. So as we can see, the tens place contains our last reported significant digit. So what we're going to do is we're going to subtract our numbers, and then we're going to round to the last reported significant decimal place, which is our tens place, because we have a 2 in our tens place. So we have 1,587 minus 120, and that gives us 1,467. Keeping in mind that we round to our tens place, we look one space to the right, we see that 7 is greater than 5, and we round up to 1,470. Do these examples make sense to everyone so far? Any questions on these examples?
Professor, for the second to last example, the 1.07 minus 0.55, you mentioned that it's okay to lose I'm sorry, I didn't catch what you said.
It's okay for you to lose significant figures. When adding and subtracting, we only care about decimal places.
Got it. Okay, thank you.
For the last example, so we round instead of to the least number of decimal places. Instead, what we're doing here is we're retaining the least number. So if you write these numbers out in scientific notation, you can use the decimal place rule. In this case, I'm showing you the shortcut that is commonly shown in your textbook, in which case you note the decimal place that contains the last reported significant digit. So for example, 120 has a digit in the tens place, while 1,587 has a digit in the ones place. So we then round to the largest place that contains the last reported significant digit. So the tens place is larger than the ones place. So we're going to round to the tens place. We subtract our numbers, and then we round our final answer to the tens place, because 120 has its last reported significant digit in the tens place. To make this easier to see, we can also write this as 1.587 times 10 to the third minus 0.12 times 10 to the third, in which case we'd get 1.467 times 10 to the third, which we could round to 1.470 times 10. Well, 1.47 times 10 to the third. And I'll showcase this method in a moment if you're more comfortable with decimals. as an example, one student wanted me to go over the following. So this is a bonus example again. So we have 10 plus 3.5. So as written, looking at 10, as written, looking at 10, 10 has its last reported significant digit in the tens place, while 3.5 has its digit in the tenths place. So we're going to add these numbers together and round to the nearest last reported place. So we get 13.5, but our largest significant place is the tens place. So we're going to round this number to the tens place, and that in turn would give us 10. This is important to note, and this is actually a really interesting example because it showcases a fundamental idea in significant figures. Depending on the number of significant figures in your measured values, you were limited in the number of digits you can report at the end of your calculations. Does that make sense? Did that address the question in the chat? Yes, we'll be doing a few more examples. Actually, I have another set. We're actually just going to talk about one other example first. So when you're dealing with numbers without a decimal point, one trick that I like to use is I write my largest number in scientific notation, and I write my other number in base 10 notation with the same power of 10. So for example, 1,750, 1, 2, 3 decimal places, that gives me 1.75 times 10 to the third. And now what I'm going to do is I'm going to take 560 and I'm just going to divide it by 10 to the third. And that in turn gives me 0.560 or 0.56, sorry about that, times 10 to the third. So now both of my numbers have the same power of 10, so I'm able to add and subtract them. As I can see, my top number has 2 decimal places. My bottom number has 2 decimal places. So my final answer should have 2 decimal places. So that in turn gives us 1.19 times 10 to the third. I like this base 10 method because it also gives you your final answer in scientific notation. And it makes it very easy for you to count the number of decimal places. Does that make sense? So you're welcome to use either method. I'm just showing you multiple methods of tackling these types of addition and subtraction operations. So, any questions? If not, let's have everyone work on a few more examples. So let's have everyone work on the following 3 examples, and we'll spend about 4 to 5 minutes working on these examples, and then we'll come together as a group to discuss. Yes, of course. We'll do this first batch of examples, and then I'll have another opportunity for students to work on even more problems. So let's try to get a few responses in the chat. And don't worry, even if you're unsure, I want you to give a first attempt at these problems. So that way, once you see the solution, you can revise your problem solving method, and then you can apply that revision to the next set of examples. It's found that even the act of attempting a problem and working through and talking yourself through a problem is very instructive in developing problem solving skills. And the responses I see in the chat look reasonable so far. Let's try to get a few more responses from the class. Let's spend about another 2 to 3 minutes on these examples. And we'll discuss momentarily. And don't worry, even the act of proposing your response is informative in completing and solving these problems. Let's try to get a few more responses in the chat, and don't worry if you're unsure. Give it your best try for this first attempt, and then we'll have an opportunity to revise and attempt one more time. And we'll discuss in about another minute to a minute and a half. Let's try to get a few more responses in the chat or verbally. And if you have a question that I can address, don't be shy to message me with your proposed questions or to unmute and ask your question verbally. The responses I'm seeing in the chat look good so far. As long as you're following sig fig rules, either methods of reporting your final answer would be correct. I see a student has another problem that they'd like us to go over. We'll address that at the end of this first set of 3 problems. One thing to keep in mind is, just like before, remember to pay attention to your placeholder digits. I see many responses with the correct number of sig figs, but are missing placeholder digits to indicate whether your number is large or small. Especially for the second example, your final answer should be on the order of thousands, right? So make sure to include those placeholder zeros. So to help give everyone some guidance, thank you everyone for sharing. The responses were definitely on the right track. Many of them were perfect, and the other responses were, the logic was very good. Okay, so let's look at this first example. We have 1.67 minus 0.71. Our first number has 2 decimal places. Our second number also has 2 decimal places. So we have 1.67 minus 0.71. That in turn gives us 0.96, a number with 2 decimal places. So we're good to go. 0.96 is a perfectly valid final answer. So for 5,300 minus 700, I'm going to use the scientific notation method, and I can write this as 5.3 times 10 to the third. And I'm going to take 700 and divide it by 10 to the third to give me 0.7 times 10 to the third. Now that both of my numbers have the same power of 10, they can be, so for the first example, you don't need to round up because this number already has 2 decimal places, as required in our final answer for this subtraction operation. Did that answer your question? Perfect. So one thing to keep in mind, you can only add and subtract numbers if they have the same power of 10. That's why we use this base 10 method. That's why I divided 700 by 10 to the third. So both of my decimals have the same power of 10. That in turn gives us 4.6 times 10 to the third. Both of our numbers have one decimal place, so our final answer should have one decimal place. This is why you really need to make sure if you're writing your numbers out long form, you need to include your placeholder zeros. This is 4,600 rather than 4.6. So make sure to include your power of 10 in your final answer. Did that make sense to everyone?
Professor,
Yes.
can you do another way, like not use the scientific notation?
Yes, I can showcase that right here. So looking, 700, our digit is in the hundreds place, and 5,300, our last digit is in the hundreds place. So that in turn, at the end of our calculation, gives us 4,600. So our final answer is rounded to the hundreds place, and as a result, our number follows sig fig rules. Yes, you can subtract them normally, but then it requires you to note what place has the last reported significant digit. So I find when you write it in scientific notation, it allows you to more easily count significant digits and count decimal places accurately. Does that make sense? Did that clarify the questions that everyone had on this example? So let's look at our last example. So we have 50.4 minus 5.46. So let me line up these numbers. As we can very clearly see, 50.4 has one decimal place. 5.46 has two decimal places. We subtract our numbers, and that in turn gives us 44.94. We need to round our final answer to one decimal place. So we look at our value, one space to the right, 4 is less than 5, so we round down, and that gives us 44.9 as our final answer. Yes, and we'll have another set of examples actually as a follow-up. Are there any questions I can address on this first batch of examples? Are there any questions I can address? Is this making a little bit more sense now that we've seen a few examples and tried working through a few examples? The responses I've seen in the chat were great, by the way. So let's do another set of examples. So I'd like you now to work on the following two examples, and as a bonus example, to address demand in the chat for another example of this long form addition, I'd like you to add 551. Let's do 557 and 30 together. So let's work on these three examples. Let's spend about 4 to 5 minutes on these examples, and then we'll come together as a group to discuss. And the responses I'm seeing in the chat look great so far. Let's try to get a few more responses and we'll discuss in about 3 to 4 minutes. And the responses I'm seeing in the chat look great so far. Let's spend another 2 to 3 minutes on this example, and don't be shy to share your responses in the chat or verbally, and don't be shy to ask questions in the chat or to unmute and ask your questions verbally. And the responses I'm seeing look great so far. Let's discuss in about another minute and a half. And the responses I see in the chat look great so far. So let's discuss now. So first and foremost, this first one is a nice example showing how you can gain significant figures when you perform an addition operation. So both of these numbers have 3 decimal places. So our final answer should have 3 decimal places. So that in turn gives us 500.356. Let's look at this next example. So we have 60.13 plus 5. We're going to put a decimal point at the end of 5. Adding up our numbers, we have a number with 2 decimal places and a number with 0 decimal places. So that in turn gives us 65.13. We round this to 0 decimal places. To do that, we look 1 space to the right. We see 1 is less than 5, so we round our final answer to 65. Finally, 557 plus 30. We can also write these in scientific notation or base 10 notation as 5.57 times 10 to the second plus 0.3 times 10 to the second. In both cases, we can clearly see that the tens place contains our last reported significant digit for 30. So we need to round to the tens place. So we get 587. If we're rounding to the tens place, we look 1 space to the right, and that in turn gives us 590. For our second example, if we're using the decimal method, we see that our top number, our first number, has 2 decimal places. Well, our bottom number has 1 decimal place. So when we get 5.87 times 10 to the second, we need to round this number to 1 decimal place. So we look to the right and round up to 5.9 times 10 to the second. Either method is acceptable in this case. Did that make sense to everyone so far? Any questions on these examples? So I see a student has another question in the chat. Allow me to switch over to a whiteboard to answer that question. So we'll do this, we'll answer this. So the answer doesn't have to be in scientific notation, no, unless I explicitly ask you for it.
For the last example,
Yes.
this is 587.
Yes.
I know we have to round the 8 to the 9, so we
Yep.
just get rid of that 7 for 590.
Yes,
I'm
because
kind of
we want our final answer to have 1 decimal place. So we're rounding to 1 decimal place.
Okay.
Does that make sense?
Yes.
Perfect. So to close out our lecture, we have a bonus example that a student asked in the chat. So I'm just going to share a whiteboard and we'll discuss this example. One student asked if we have 10 dot plus 3.5, what would our final answer be? So let me rewrite this. Whoops, that's a little. So 10 dot plus 3.5, we have a number with 0 decimal places plus a number with 1 decimal place. Adding them together, we get 13.5. So we need to round this number to 0 decimal places. So that in turn means we look 1 space to the right, and that gives us 14. Did that address the question in the chat? Perfect. I'm just going to clear this. You don't need to put a decimal after because 4 is a significant digit. So this is a good place for us to stop. So we're going to pause